Okay, we can start now. Welcome to the webinar titled Technology Assessment of Energy Efficiency Measures and Review of Financial Supports for Energy-Intensive Industries, organized by the Audit Plus project for energy-intensive companies based in Ireland. The webinar is divided in two parts. In part one, after introducing the Audit Plus project and integral consultancy service developed under the project, we will cover the prioritization of energy efficiency measures and the implementation checklists for such measures. In addition, part one presents the support scheme for renewable heat, along with key technical aspects related to heat recovery from refrigeration systems and heat recovery from chiller plants using heat pumps. Part two focuses on industrial heat demand and the most suitable technologies for delivering heat within specific temperature ranges. It includes a comparison of technologies for industrial heat applications and an overview of relevant financial supports, such as the EXCEED grant, the air handling units for business heat recovery, and upgrade grant, solar PV systems, and notes on alternative of complementary technologies for solar PV. It also covers guidance on PV system design and about the non-domestic microgeneration grant. So the Audit Plus project was launched in October 2023 to establish, coordinate, and evaluate the impact of multi-stakeholder local groups at the EU level, acting as a single intermediary for energy-intensive industries, implementing energy efficiency measures following an energy audit. The project set up working groups in 4 industrial regions in Ireland, Poland, Spain, Castellón, and Galicia, across the EU, and examined the current gaps and needs to enhance the impact of energy audits conducted in energy-intensive industries. Existing technical and regulatory knowledge on implementing the energy efficiency measures and renewable energy generation has been translated by the project into practical know-how and shared with up to 2,000 value chain stakeholders. The project has introduced an integral consultancy service that is contributing to reduce the energy intensity of industrial processes by at least 10% across a number of energy-intensive industries involved, and with envisaged the savings of more than 300 gigawatt-hour per year. We also involved the policymakers, industry associations, private companies, technology experts, and brought them together to develop new standards and financial mechanism to boost investment by energy efficiency, the energy-intensive industries in implementing the energy efficiency measures identified by the audits. The integral consultancy service is a service that comprises 7 sub-services. So this is delivered by the Audit Plus project and includes the following components: technology assessment, cost-benefit analysis, engineering support, identification of financing, for public and private sources for financing, matchmaking with technology and service providers, guidance for implementing measures after audit plans, and support to develop corporate energy strategy. So if any energy-intensive industry is interested in these services, they can contact the Audit Plus team. Now let's move to the technical part. So First topic is prioritization of energy efficiency measures. In energy-intensive industries, energy efficiency and decarbonization measures should be prioritized using a hierarchical approach that seeks to maximize energy savings and emission reductions while minimizing capital expenditure, operational disruption, and implementation risk. By addressing the most cost-effective opportunities first, organizations can achieve immediate reductions in energy consumption and operating costs while creating a foundation for more substantial long-term investment. The first priority should be the elimination of avoidable energy waste through operational optimization and improved asset management. These measures typically require limited capital investment and offer rapid payback periods. Examples of these include reduction of energy waste through improved shutdown procedures, elimination of unnecessary equipment operation, optimization of production schedules, and reduction of standby power consumption. Reduction of hot water waste by identifying and eliminating unnecessary hot water use, repairing leaks, improving insulation, and reducing distribution losses. Enhanced maintenance programs to ensure that equipment operates at optimal efficiency. Identification and elimination of compressed air, steam, water, and thermal energy leaks. Improved the process scheduling to minimize peak energy demand and equipment idling. These measures often provide the lowest cost route to energy savings and should be implemented before considering capital-intensive projects. Following the elimination of obvious waste, organizations should focus on improving energy management practices and operational controls to sustain and enhance efficiency gains. Examples include staff training and awareness programs focused on energy efficient operation, installation of energy monitoring and sub-metering systems to identify inefficiencies and track performance, automated controls, and smart energy management systems that optimize equipment operation based on demand. Hot water temperature optimization, ensuring temperatures are maintained only at levels required for operational and hygiene requirements. Process temperature optimization, reducing heating requirements where product quality and process performance allow. These measures improve visibility of energy consumption and enable continuous optimization across industrial operations. Once operational efficiencies have been maximized, organizations should evaluate opportunities to improve the efficiency of core equipment and process systems. Examples include replacement or retrofit of inefficient motors, pumps, compressors, fans, and HVAC systems, installation of variable speed drives and advanced process controls, upgrading insulation, pipework, and heat distribution systems, modernization of heating equipment to improve thermal efficiency. Such investments typically require moderate capital expenditure but can deliver substantial and sustained reduction in energy consumption. After minimizing energy demand, attention should shift towards recovering and reusing energy that would otherwise be lost from industrial processes. Examples include waste heat recovery from process exhaust streams, cooling systems, refrigeration systems, or wastewater, installation of heat exchangers and economizers to capture and reuse thermal energy, mechanical vapor recompression systems for evaporation and concentration processes, integration of recovered heat into hot water generation or process heating applications. Heat recovery measures can significantly reduce fuel consumption by displacing primary energy requirements with recovered energy. With demand reduced and waste heat recovery maximized, facilities should assess opportunities to replace fossil fuel-based heating systems with more efficient electrical technologies. Examples include heat pump integration to upgrade low-grade waste heat and provide process heat, hot water, or space heating, electrification of thermal processes where technically and economically feasible, expansion of electric heating technologies to replace direct fossil fuel combustion. Heat pumps are particularly attractive because they can deliver multiple units of thermal energy for each unit of electricity consumed, significantly improving overall system efficiency. Once that energy demand has been optimized, renewable energy generation and alternative fuels can be deployed to reduce remaining carbon emissions. Examples include solar PV installation to generate renewable electricity and offset grid consumption, wind to heat implementation or expansion using renewable electricity from wind generation to directly supply thermal energy demands, biomass heating systems for renewable thermal energy generation where sustainable fuel supplies are available, biogas boilers to replace fossil natural gas in existing heating infrastructure. At this stage, renewable energy systems are more effective because overall site energy demand has already been reduced, improving the economics of renewable deployment. The final stage involves transformational projects that fundamentally redesign energy systems and industrial processes to achieve deep decarbonization and long resilience. Some examples are process redesign and intensification to reduce energy demand, integration of high efficiency combined heat and power systems, CHPs, where appropriate, organic Rankine cycles technologies for converting waste heat into electricity, large-scale renewable energy integration and energy storage solution, site-wide utility system optimization and thermal network redesign, HVO, hydro-treated vegetable oil backup systems to provide lower carbon energy or standby generation where electrification is not yet feasible. These projects typically involve significant capital investment and longer implementation timelines, but can deliver substantial reductions in both operating costs and greenhouse gas emissions. By progressing through this hierarchy from waste reduction and operational optimization to renewable energy integration and measured capital projects, industrial facilities can maximize the return of investment of energy efficiency measures while establishing a practical and cost-effective pathway toward long-term sustainability and net zero objectives. A technical implementation checklist for energy efficiency measures in energy-intensive industries should ensure that proposed energy saving and decarbonization measures are correctly designed, integrated, installed, commissioned, and verified to deliver the anticipated energy cost and emissions benefits. While the specific requirements vary depending on technology being implemented, the checklist should provide a structured framework covering engineering, operational, safety, and performance aspects throughout the project life cycle. Before implementation, it is essential to establish a clear understanding of current operating conditions and energy performance. Key activities for this include define system boundaries and identify affected processes, utilities, and equipment, establish baseline energy consumption, fuel use, thermal loads, and operating profiles, verifying production rates, operating schedules, and seasonal variations, quantify current electricity, hot water, steam, and fuel consumption, identify operational constraints and critical process requirements, confirm expected energy savings, carbon reductions, and performance targets for measures such as reduction of electricity waste, reduction of hot water waste, and temperature optimization. A detailed baseline is critical to accurately measure the improvements. The detailed engineering design should be reviewed to ensure that the proposed solution is technically feasible and capable of achieving the intended performance. Key checks include verification of energy and mass balance calculation, confirmation of equipment sizing and capacity requirements, review of thermal and electrical load calculations, assessment of process integration impacts, verification of pipework, ductwork, hydraulic and electrical designs, confirmation of equipment specifications, and performance guarantees. Particular attention should be given to waste heat recovery systems, ensuring sufficient heat sources and heat sinks are available, heat pump integration, confirming source temperatures, sink temperatures, coefficient of performance, and operating profiles, solar PV systems, validating electrical connection arrangement, inverter sizing, and export limitations, wind-to-heat systems verifying renewable generation profiles and thermal storage requirements, biomass and biogas heating systems confirming fuel quality, storage requirements, combustion design, and emissions compliance. Implementation should confirm that supporting infrastructure can accommodate the proposed measures. Key checks include available electrical network capacity, transformer and switchgear loading, steam system capacity and pressure stability, hot water system capacity and circulation performance, cooling water and chilled water availability, compressed air requirements, fuel supply and storage capacity. Other examples include assessing electrical network impacts associated with heat pump integration, confirming grid connection requirements for solar PV, verifying fuel handling and storage infrastructure for biomass heating, biogas boiler, and HVO backup system, evaluating thermal storage requirements for wind to heat applications. All the energy efficiency measures should be assessed for their interaction with the existing industrial processes. Key checks include identification of process interfaces, impact on production throughput, and product quality, process control interactions, thermal balance impacts, startup and shutdown requirements, operational flexibility considerations. Examples include ensuring process temperature optimization does not adversely affect the product quality or process stability, verifying that waste heat recovery system do not create excessive process pressure drops or operational bottlenecks, confirming that heat pumps can meet variable thermal loads throughout the year. Some comments about instrumentation, controls, and monitoring are so effective monitoring and control are essential to achieve and sustain expected energy savings. Key checks include the installation of appropriate energy meters and submeters, calibration of temperature, pressure, flow, and energy measurement devices, verification of communication systems and data acquisition, integration with SCADA or building management systems, development of energy performance dashboards and reporting tools, alarms and fault management configuration. Particular attention should be given to monitoring systems supporting electricity waste reduction initiatives, temperature controls associated with hot water temperature optimization and process temperature optimization, performance monitoring for heat pumps, waste heat recovery systems, and renewable energy assets. During the construction and installation, quality assurance procedures should verify compliance with design specifications. Key checks include mechanical installation inspections, electrical installation inspections, verification of pipework, insulation, and ductwork quality, equipment alignment and mounting checks, verification of fuel handling systems, inspection of pressure systems and safety devices, compliance with relevant engineering standards and codes, Specific examples include heat exchanger installation quality for waste heat recovery systems, refrigerant system integrity for heat pump installation, structural mounting inspection for solar PV arrays, fuel storage and handling inspections for biomass, biogas, and HVO systems. All projects should undergo appropriate safety reviews before commissioning. Key checks includes process hazard analysis or and review where applicable, fire and explosion risk assessment, electrical safety verification, pressure system compliance, fuel storage and handling safety assessment, environmental permitting requirements, emissions compliance verification. Additional considerations include combustion safety for biomass heating and biomass boilers, refrigerant safety and containment requirements for heat pumps, fuel management procedures for HVO backup system, electrical protection and isolation arrangement for solar PV installation. Commissioning activities should demonstrate that the system performs safely and according to design intent. Key checks include mechanical completion verification, control system functionality testing, equipment startup and shutdown testing, safety interlock testing, control loop tuning and optimization, verification of operating sequences, operator training and documentation review. Examples include verification of heat recovery effectiveness under varying process loads, heat pump performance testing across expected operating ranges, solar PV generation verification against design output, biomass and biogas combustion performance testing, wind to heat control and thermal storage system testing. Following commissioning, actual performance should be validated against the design assumptions. Key checks include measurement of energy savings achieved, verification of fuel consumption reductions, carbon emissions reduction assessment, comparison of actual versus predicted performance, identification and correction of performance gaps, development of long-term monitoring plans. Examples include validation of electricity reduction from waste elimination measures, confirmation of hot water consumption reductions, verification of temperature optimization savings, assessment of waste heat recovery utilization rates, heat pump COP verifications, renewable energy generation verification for solar PV and wind to heat systems, fuel displacement verification for biomass, biogas, and HVO systems. The final stage should ensure that the implemented measures continue to deliver benefits throughout their operational life. Key activities include development of operating procedures, maintenance planning and scheduling, operator training programs, energy performance review processes, periodic recalibration of instrumentation, ongoing monitoring and optimization. Continuous performance review is particularly important for measures such as waste heat recovery, heat pumps, renewable energy systems, and temperature optimization initiatives where operating conditions can significantly influence long-term performance. By applying these structured implementation checklists, the organizations can reduce technical risks, improve project outcomes, maximize energy savings, and ensure that energy efficiency and decarbonization measures deliver their intended operational, financial, and environmental benefits. Now, the support scheme for renewable heat is one of the supports reviewed in this presentation, this webinar. So the Sustainable Energy Authority of Ireland, is SEI, Renewable Heat Support Scheme, is a government-funded initiative designed to accelerate the adoption of renewable heating technologies across the industrial, commercial, agricultural, and public sectors. The scheme aims to reduce reliance on fossil fuels, lower greenhouse gas emissions, and contribute to Ireland's national renewable energy and climate targets by supporting the transition to low carbon heat generation. To qualify for support under the scheme, projects must involve the replacement or displacement of fossil fuel-based heating systems with eligible renewable heating technologies. The renewable heat generated must be used for a legitimate heat demand, such as space heating or industrial process heating. Supported systems must comply with applicable eco-design and efficiency standards, and the design and installation must meet all relevant building regulations, environmental requirements, and technical standards. The applicants are expected to engage suitably qualified and competent designers, installers, and contractors to ensure system performance and compliance. In addition, organizations must satisfy SEI's administrative requirements, including demonstrating financial solvency and maintaining a valid tax clearance certification in order to be eligible for grant payment. The Renewable Heat Support Scheme includes two primary support mechanisms: an operational tariff scheme for biomass heating systems and biogas boilers, and a capital grant scheme for commercial heat pumps. The tariff scheme supports the installation and operation of eligible biomass boilers and anaerobic digestion biogas heating systems that replace fossil fuel-based heat generation. Under this mechanism, participants receive ongoing payments based on the amount of renewable heat produced and used for eligible purposes such as space heating or industrial process heating. The objective of the tariff is to bridge the operating cost gap between renewable and conventional fossil fuel heating systems, thereby improving the financial viability of renewable heat projects. Payments are typically linked to metered renewable heat output and are made over a defined support period subject to compliance with the scheme requirements. Eligible projects must demonstrate that renewable heat displaces fossil fuel consumption and must comply with sustainability, emissions, metering, and operational performance requirements. The Commercial Heat Pump Grant Scheme provides upfront capital funding towards the installation of eligible heat pump systems in commercial, industrial, agricultural, public sector, and other non-domestic buildings. The grant is intended to reduce the initial investment cost associated with heat pump technology and encourage the electrification of heating systems. Eligible projects generally involve replacing fossil fuel heating systems with efficient heat pumps that provide space heating, hot water, or process heating. Funding is typically based on the capacity and performance of the proposed heat pump system and may cover a proportion of eligible project costs. Applicants must demonstrate that the heat pump is appropriately designed for the building or process, meets minimum efficiency requirements, and complies with relevant technical standards and regulations. Together, these support mechanisms aim to accelerate the adoption of renewable and low-carbon heating technologies, reduce greenhouse gas emissions, improve energy efficiency, and support Ireland's transition towards a more sustainable and decarbonized heat sector. The support scheme for renewable heat offers tariff support to eligible biomass and biogas installations that generate usable renewable heat and supply it for approved end uses such as space heating or process heating in commercial, industrial, agricultural, district heating, and other non-domestic applications. A key feature of the scheme is that it provides technology-specific tiered payments based on amount of renewable heat produced annually. This structure is designed to improve project viability while reflecting economies of scale, with higher support rates for smaller installations and lower marginal rates for larger systems. These payments are calculated based on verified renewable heat output, incentivizing efficient operation and accurate metering of energy production. The decreasing tariff structure ensures that smaller projects receive stronger financial support per unit of heat, helping to overcome higher relative capital and operational costs, while larger systems benefit from economies of scale. Um, Eligibility is restricted to non-emission trading system, non-ETS, ET users, including commercial, industrial, agricultural, district heating operators, and other eligible non-domestic sectors. This ensures that the scheme targets sectors where decarbonization incentives are most needed and where fossil fuel displacement can deliver meaningful emissions reductions. The application process is structured and sequential. Interested applicants must submit an application through the SEI online system. Then the application is evaluated, and if approved, a letter of offer is issued, and a grant agreement outlining the terms and condition of the support. The applicant proceeds with installation and commissioning of the renewable heat systems. Upon completion, the applicant notifies SEI and undertakes verification checks, including confirmation of compliance, metering arrangements, and eligible heat production. Once verified, operational support payments are made based on measured renewable heat delivered. Overall, the support mechanism is designed to provide a long-term revenue certainty for renewable heat producers, thereby reducing investment risks and accelerating the transition away from fossil fuel-based heating systems. Okay, so the air source heat pumps, ground source heat pumps, and water source heat pumps are all eligible under the support scheme for renewable heat. Air source heat pump extract heat from ambient air and are generally the most flexible and widely applicable option. They are particularly well suited to retrofit projects, commercial buildings, and light industrial applications where heating demand is moderate and variable. Their performance is influenced by outdoor air temperature, which means efficiency typically decreases under colder periods, leading to higher electricity consumption in winter. Despite this limitation, air source heat pumps are relatively simple to install, require minimal site preparation, and do not depend on specific geological or water resources, making them the most practical solution for constrained or urban sites. However, considerations such as external unit placement, noise, and reduced efficiency at low temperatures may require careful design and integration with backup heating systems. Ground source heat pumps extract heat from the ground through boreholes or horizontal loops and provide more stable and typically higher efficiency performance due to relatively constant subsurface temperatures. They are best suited to buildings or industrial sites with high and relatively continuous baseload heat demand, such as hospitals, large commercial facilities, or industrial processes operating year-round. This stability makes them particularly attractive for application where long-term efficiency is prioritized over lower upfront costs. However, ground source heat pumps involve higher capital expenditure, more complex engineering design, and longer development timelines due to drilling requirements and detailed ground thermal assessment. Their feasibility is strongly dependent on site conditions, including available land area, geological suitability, and ground thermal conductivity, which can limit applicability in dense urban environments. Water source heat pumps utilize heat from surface water bodies or groundwater sources and can achieve very high efficiencies due to the stability of water temperatures throughout the year. They are especially suitable for large-scale installations, district heating systems, or industrial facilities located near rivers, lakes, or suitable aquifers. Their performance can be comparable to or even exceed ground source heat pumps in certain conditions, but they are highly site dependent. Practical constraints include the need for abstraction and discharge permits, environmental assessments, and ongoing management of water quality issues such as fouling or corrosion. These regulatory and technical requirements mean that water source heat pumps are generally most appropriate for integrated energy systems or location with readily available or reliable water resources. In summary, air source heat pumps offer the greatest flexibility and lowest barriers to deployment, but with more variable efficiency. Ground source heat pumps provide the most stable and efficient long-term performance where site conditions allow, and water source heat pumps offer high efficiency but are constrained by water access and regulatory complexity. Under the support heat scheme, renewable heat scheme, the optimal choice should be based on a combined assessment of heat demand characteristics, required temperature levels, site constraints, grid capacity, alongside the opportunity to enhance system performance through complementary energy efficiency measures supported by this scheme. The support scheme for renewable heat provides an installation grant of up to 40% of eligible investment costs for renewable heating systems, and an additional grant of up to 30% may also be available for complementary energy efficiency measures such as heat recovery, ventilation upgrades, and improvements to building fabric. Heat recovery from refrigeration system is based on capturing the waste heat that is normally rejected at the condenser of the system and repurposing it as a useful heat source. In a conventional refrigeration cycle, heat is absorbed at low temperature in the evaporator and rejected at a higher temperature at the condenser. This rejected heat is often discharged to ambient air via air-cooled condenser or to cooling water systems. By integrating a heat exchanger into the condenser side, this otherwise wasted thermal energy can be recovered and upgraded for useful heating applications, such as space heating, hot water production, or low to medium temperature process heating. In many retrofit applications, the heat recovery unit is installed in series with the existing condensers so that heat recovery is prioritized when there is a heating demand, while the standard condenser rejects any surplus heat when recovery is not required. On the refrigerant side, the hot, high-pressure refrigerant leaving the compressor passes through the heat exchanger before or instead of entering a conventional air-cooled or evaporative condenser. On secondary side, a water loop is circulated through the heat exchanger, absorbing heat from the refrigerant and transferring it to a usable hot water circuit. This water circuit is then connected to a buffer tank or directly to heating or process systems, depending on demand profile and system design. The amount of heat that can be recovered is closely linked to the refrigeration system's coefficient of performance. The COP defines the ratio of useful cooling output to electrical input, and by energy balance, the rejected heat is the sum of both. For example, if a system has a COP of 3, it produces 3 units of cooling for every 1 unit of electrical energy consumed, meaning that approximately 4 units of heat are rejected at the condenser, 1 unit input plus 3 units extracted from the cooled space. However, the actual usable recovery is limited by heat exchanger effectiveness, which defines how closely the recovery heat approaches the maximum theoretical heat rejection. Typical effectiveness values range from about 50 to 85%, depending on design, fouling, temperature approach, and flow rates. The temperature of the recovered heat is primarily determined by the condensing temperature of the refrigeration system, which is itself a function of ambient conditions and system design. Since the condenser operates at a temperature higher than the desired heat sink, the recovered heat is usually available at medium temperature levels, typically in the range between 30 to 45 Celsius degrees for standard refrigeration and air conditioning systems, although higher temperatures may be achievable in some industrial systems. This recovered heat has a wide range of applications, particularly where low to medium temperature heat demand exists continuously or seasonally. Common uses include domestic hot water production in commercial buildings, space heating via low temperature heating circuits or underfloor systems, preheating or processed water in food, beverage, and pharmaceutical industries, and heating of washdown water or cleaning systems. In industrial settings, it can also be used to preheat boiler feed water, reducing fuel consumption in conventional boilers. In some configurations, refrigeration heat recovery can be combined with thermal storage to decouple heat supply from cooling demand, improving overall system flexibility and energy utilization. Heat recovery from refrigeration systems can be implemented using several types of heat exchangers selected based on temperature levels, fouling risk, pressure constraints, and whether the recovered heat is transferred to water, air, or another process fluid. Shell and tube heat exchangers are commonly used in industrial refrigeration heat recovery, where robustness and tolerance to higher pressure or fouling are important. They consist of refrigerant flowing through tubes, while the secondary fluid, typically water, flows around them in a shell. They are suitable for medium to large systems and can handle relatively high heat duties, but they are less compact and generally less thermally efficient than plate designs. Plate heat exchangers are widely used where high thermal efficiency and compactness are required. They consist of stacked corrugated plates that create alternating channels for refrigerant and water. Their high turbulence promotes excellent heat transfer, allowing for smaller temperature differences between streams. They are particularly effective in water-based heat recovery from refrigeration systems, but can be more sensitive to fouling and may require better fluid quality control. Air-cooled heat exchangers are used when heat is recovered directly into air rather than water. In refrigeration heat recovery, this is less common for primary recovery, but can be used where hot air is needed for space heating or drying applications. They are simpler in concept, but generally less efficient due to lower heat transfer coefficients on the air side, requiring larger surface areas. Double pipe heat exchangers consist of one pipe inside another, with one fluid flowing through the inner pipe and the other in annulus. They are simple, relatively inexpensive, and easy to maintain, making them suitable for small-scale or pilot systems. However, they are not typically used for large heat recovery duties due to limited surface area and lower and compactness. The sizing of any heat exchanger for refrigeration heat recovery is fundamentally based on the heat duty and log mean temperature difference method. The heat duty is determined from the available condenser heat rejection, which is linked to the refrigeration system's cooling load and COP. Once the required heat transfer rate is known, the heat exchanger size is calculated using the equation Q equals U times A times LMTD, where Q is the heat transfer rate, U is the overall heat transfer coefficient, A is the heat transfer surface area, and LMTD is the logarithmic mean temperature difference between hot and cold streams. The LMTD method accounts for the fact that the temperature difference between the refrigerant and the heating water changes along the length of the exchanger. And it is calculated using the inlet and outlet temperature differences between the two streams, providing an average driving force for the heat transfer. As more temperature approach closer inlet and outlet temperatures between fluids increases efficiency, but requires a large heat exchanger area. Conversely, a large temperature difference reduces the exchanger size, but limits the heat recovery efficiency. Heat recovery from chiller plant using a heat pump. Heat recovery from a chiller plant or refrigeration system using a heat pump is based on capturing low-grade waste heat from the condenser loop and upgrading it to a higher, more useful temperature level. In a typical chiller plant, it is rejected at the condenser into cooling water loop or dry cooler circuit at temperatures commonly in the range of about 30 to 45 Celsius degrees. This heat is usually discharged to ambient condition, even though it still contains significant usable energy. A heat pump can be integrated into this system to recover heat and lift that heat to a higher temperature suitable for end-use applications. The heat pump effectively acts as the temperature booster. It takes the relatively low temperature condenser return water and its source as its source, and using electrical energy to drive a compressor cycle increases the temperature of the recovered heat to a usable level. Depending on the design and refrigerant selection, this upgraded heat can reach around 60 or higher for space heating applications, and in high temperature industrial heat pump systems, it can exceed 90 degrees Celsius for process heating or hot water systems. The key principle is that the heat pump does not create heat from electricity alone, but instead upgrades existing waste heat, making the overall process significantly more efficient than direct electrical heating or fossil fuel boilers. In operation, the heat pump is typically connected in parallel with or integrated into the chiller condenser loop. When there is simultaneous cooling and heating demand, the system becomes particularly efficient because the chiller continues to reject heat into the condenser loop while the heat pump extracts and upgrades it. In this configuration, the cooling process effectively provides the free heat source, and the heat pump only supplies the additional energy needed to raise the temperature. This results in a high overall coefficient of performance, often significantly higher than standalone heating systems, because the system benefits from heat that would otherwise be wasted. The recovered and upgraded heat can then be used to displace conventional boiler operation, reducing fossil fuel consumption and associated CO2 emissions. Typical applications include space heating systems, domestic hot water production, industrial process heating, such as washing, pasteurization, cleaning systems, or low to medium temperature process loops. In industrial settings, this approach is particularly valuable where there is a constant or coincident demand for cooling and heating, such as in food processing, pharmaceuticals, data centers, and manufacturing facilities. Integrating a heat pump with a chiller plant transforms the system from a purely cooling-focused installation into a combined heating and cooling energy system by upgrading condenser waste heat from approximately 30 to 45 Celsius degrees to useful heating temperatures up to 60 degrees or even higher. It maximizes the energy recovery, improves the system efficiency, and enables significant reductions in boiler-related fuel use. A heat pump can be integrated with a chiller plant by connecting it directly into the condenser water loop, allowing waste heat from cooling processes to be upgraded and reused for useful heating within an industrial facility. The key principle is to divert part of all of the low-grade heat rejected by the chiller condenser into the evaporator side of a heat pump rather than rejecting it fully to a cooling tower or dry cooler. In a conventional chiller plant, the condenser rejects into a circulating water loop. This loop leaves the chiller at around 35 to 40 degrees, normally returns cooled water at approximately 32, 38 after its rejection in cooling towers or dry coolers. When a heat pump is added, this condenser water loop becomes available low temperature heat source. A portion of the flow is directed through a heat exchanger or directly through the evaporator of the heat pump, where heat is absorbed by the condenser water. As a result, the water leaving the heat pump evaporator is cooling slightly further with the acceptable range of the loop, helping maintain the condenser return temperature typically around 32, 38. This ensures that the chiller plant continues to operate within its normal design conditions while simultaneously supplying usable low-grade heat to the heat pump. On the heating side, the heat pump condenser is connected to a separate heating water circuit serving the industrial facility, and this circuit is supplied with water at approximately 55 to 6 Celsius degrees, which is suitable for space heating, domestic hot water preheating, and many low to medium temperature industrial processes. The return water from the building typically comes back at around 45, 50 Celsius degrees, depending on the heating system design and load conditions. The heat pump then upgrades the temperature difference between the low-grade condenser water loop as the heat source and the higher temperature heating loop as the heat sink, effectively lifting waste heat to a usable level. The critical design concept in this configuration is simultaneously balancing the temperature levels. The chiller condenser loop provides a stable low temperature heat source at 35 Celsius degrees. The heat pump extracts energy from this loop and at the same time raises the extracted energy to a higher temperature level, such as 55 to 60 on the heating side. This is creating a cascade effect where cooling demand generates recoverable heat and the heat pump bridges the temperature gap between waste heat and useful heat. The system is typically controlled so that heat recovery is prioritized when there is concurrent cooling and heating demand. When the heating demand is low, excess condenser heat is still rejected through the cooling tower or dry cooler to maintain system stability. When heating demand is high, more of the condenser heat is diverted through the heat pump, reducing or eliminating the need for boiler operation. This integration significantly improves overall plant efficiency by utilizing energy that would otherwise be wasted, while also reducing fossil fuel consumption and improving the combined coefficient of performance of the cooling and heating system. Okay, so this ends the first part of the webinar. Thanks very much for attending. I think we will have a few minutes break and then start with the second part. Thank you.
Thank you, Luciano.
Thank you.